So, we gather here today to celebrate physics in memory of Oskar Klein. The idea here is that I will say a few words about him and his role in physics. I'm Bo Sandborg, by the way, professor here at Physicum. Now, after that, Laurus Thorlasius will take over and introduce our speaker today. And there will be a small ceremony after that. We shifted that to before the talk, so we can have an uninterrupted celebration with a talk and questions. So let's start. Yes. So, Oskar Klein, he was a Stockholm physicist in my grandmother's generation. More importantly, he was a young physicist in Copenhagen in the 20s when modern physics was born. And he was not just a spectator. He contributed to many important developments, important still today. Kaluza-Klein theory, the Klein-Gordon equation, Jordan-Klein second quantization, the Klein-Nishina formula, and the Klein paradox. For today's lecture, the Klein paradox is possibly the most relevant. So what are paradoxes for? They aren't possible to measure in the lab, are they? Paradoxes disclose the tension between accepted principles. So physics thrives on this tension. It challenges our theories and directs our attention for the future. On Christmas Eve, 90 years ago, Oskar Klein's manuscript on his paradox was received by the journal Zeitung für Physik. It dealt with relativistic particles in an external potential. Intense debate followed. Today, this paradox, as it was called, is resolved, but is still relevant. The most relevant aspect of it is the connection to Hawking radiation from black holes, which I turn to now. This is supposed to depict this potential step, right? In a sufficiently strong potential, pairs of particles and antiparticles are created. This happens outside the event horizon of a black hole. And as I said, this creation of particles and antiparticles is part of the resolution to the Klein paradox. The particles in the pair, they are correlated with one another, and if one of them is absorbed by the black hole, Hawking argued that information would be lost. This is in tension with basic quantum mechanics and constitutes the information paradox. So our speaker today has played a decisive role in this resolution, in the resolution of the information paradox, and it's very suitable thus to have him in our list of eminent Klein lecturers. Now I leave the word to Laurus Thorlasius, who's going to chair the session.
Thank you. So, on behalf of the Oskar Klein Memorial Lecture Committee, it gives me great pleasure to introduce the speaker for the 2018 Oskar Klein Lecture, Professor Leonard Susskind from Stanford University, who will also receive the 2018 Oskar Klein Medal here today. Professor Susskind is a world-renowned theorist who has made key contributions to many branches of physics. He has made contributions to elementary particle physics, to string theory, and to quantum gravity. He received his PhD from Cornell University in 1965. This was followed by a postdoctoral fellowship at Berkeley, and then since 1967, he joined the faculty of Yeshiva University in New York. And then since 1978, he has been at Stanford University, where he is the Felix Bloch Professor of Physics. Now, Professor Susskind's list of physics achievements is quite long, and I will just list or mention a few highlights. He did groundbreaking work on the theory of quark confinement. He has also on lattice gauge theory, had a very early theory of baryogenesis in the early universe, and he's also one of the originators of the so-called technicolor theories of electroweak symmetry breaking. He was one of the founders of string theory in the late 1960s, and string theory and quantum gravity have been major themes in his research throughout. Among his many seminal contributions to gravitational theory and string theory, I think stands out is the holographic principle, which among other things underlies Maldasena's celebrated anti-de Sitter conformal field theory, ADS-CFT correspondence. And his recent work has focused on the application of ideas from quantum information theory, quantum computing, such as quantum complexity, to the physics and thermodynamics of black holes and other holographic systems. And I believe we'll hear more about this in his talk this afternoon. In addition to his research accomplishments, Susskind is highly regarded as an educator, and he's an ambassador of physics to the general public. He has written several textbooks, books on popular science, and you will find many of his lectures online. He's a member of the US National Academy of Sciences, the American Academy of Arts and Sciences. He was awarded the Sakurai Prize in 1998, the Pomeranchuk Prize in 2008, and now in the 2008 Oskar Klein Medal. And so before we start the talk, I would like to yield the floor to my colleague Edward Mertzal, who will present the Klein Medal, and then we will continue with the proceedings.
Okay, thank you very much. So I will be very brief. I will basically just hand over the medal, but first I will take this opportunity also to invite you to a reception after the talk. So this will be on the third floor outside of the restaurant. I don't know if I can. Can I? Yeah, I will just hold it closer, so I will do it manually. Okay, is that fine? Good. Okay, so I have the medal here, so please, Leonard. It's a pleasure to hand you the Oskar Klein medal. Thank you. So there you go. I will. So in case you didn't catch it, this was actually the thing you saw on Bo's first slide there. Okay.
Well,
so
okay.
Now I give the floor
Good.
to you.
Thank you.
Thank you.
All right. About 25 hours ago, I woke up in Palo Alto. I have not been asleep since. I can handle that, being up for 25 hours. Not as well as I could when I was 20 years younger, but it's a dangerous thing to do before you give a public lecture. I don't expect to fall asleep, but I think it's quite possible that I won't recognize some of my own slides up there. So if I start to ramble and get a little bit incoherent, well, I'll just ask you to forgive me, because I'm pretty tired. I wonder if I have some friends here. Paolo De Vecchio, is he here? Hello, Paolo. How are you? Long time. Okay. Okay, let's begin. I had some things I was going to say about Oskar Klein, in particular the connection between the Klein paradox and Hawking radiation. I've been scooped. Too late. Nevertheless, I will say in many different circumstances, my career has crossed paths with Oskar Klein's. In particular, that's the one I wanted to most emphasize. But I'll leave it to Boo to have said that. Anyway, let's begin. Let's see, how does this work? What I want to talk about with you today is quantum mechanics and gravity. As was mentioned, that's been a subject which I've been interested in for a long time. In fact, I would say it's the only subject I've been interested in for a long time, a physics subject. Let me begin with a question. This is too small to see here. Is gravity a thing to be quantized like the harmonic oscillator? Is gravity a thing to be quantized like the harmonic oscillator, the hydrogen atom, electrodynamics, or Yang? Oh, there it is. I got it. Okay, good. Thank you. Is gravity a... Can we move this over here so I can stand in front of it? Is this going to work? No. Maybe we can move the whole table over. Good. Yeah, okay, good. Okay, good. Yes, is gravity a thing to be quantized? Quantized is a particular recipe. It's a recipe for taking a classical system, a classical theory of some kind, and to convert it into a quantum mechanical theory. It's a recipe that goes back to Dirac, and it consists of a number of steps. The first step is you take the degrees of freedom, in this case the gravitational field, the metric of space-time, and you replace it by operators. Operators, quantum mechanical operators. And then you invent a thing called a Hilbert space. A Hilbert space replaces the phase space of classical mechanics. You replace you replace Poisson brackets by commutators. This is just a recipe. And finally, Hamilton's equations of motion, become the Heisenberg equations of motion. The important thing here is that there is a recipe for taking a classical theory and converting it to a quantum theory. You can do it other ways. There's the path integral approach of my friend Richard Feynman. What's the usual goal? The usual goal is to construct a set of Feynman diagrams. Diagrams that will allow you to calculate processes like, for example, the scattering of particles due to gravitational forces, the scattering of light by the sun, all kinds of processes that you can calculate quantum mechanically. And to some extent it works, but not so well. Once you start actually trying to use it and trying to push it to its logical conclusions, all hell breaks loose. Everything comes out infinite. Black holes lose information. All kinds of bad things happen that aren't supposed to happen. And so I would say, to some extent, or perhaps to more than some extent, it's been a failure. The quantization of gravity as if it were just a classical theory to apply the recipe to. Okay, well, this has led some people to say, more than some people, almost everybody, to think that there's some really serious tension or even a contradiction between gravity and quantum mechanics. I want to read you what I had to say about this. I'm reading now what's in quotes there I've taken from my own writings. I take exception to this view. Oh, incidentally, to take exception to something in English means I just don't agree with it. I take exception to this view. I think exactly the opposite is true. It may be too strong to say that gravity and quantum mechanics are exactly the same thing, but to those of us who are paying attention, we may already sense that the two are inseparable, that neither makes sense without the other. And two things make me think so. I'm going to describe those two things today and go into some detail, not technical detail, but conceptual detail. The first of them is called ER equals EPR. I'll tell you right now, I hadn't intended to tell you now, but I'm going to tell you anyway. ER stands for Einstein and Rosen. Einstein and Rosen, well, you've heard of Rosen, but Einstein was sort of his assistant. I am tired. Stands for Einstein and Rosen, who wrote a famous paper about gravity in 1935. EPR stands for Einstein, Podolsky, and Rosen. Podolsky was another one of Einstein's collaborators who wrote a famous paper about quantum mechanics that same year, 1935, having little idea, I suspect, I don't believe they had any idea, that the two were intimately related. Einstein-Rosen and Einstein-Podolsky-Rosen. Now, what are they? We're going to spend a little bit of time explaining what they are and how odd and bizarre they are. Let's start with the idea of a formation of a black hole. Very simple. A cloud of particles, indicated by a bunch of little points, collapses under its own weight due to its own gravitation. The particles get pulled together by gravity, and what happens to them? Eventually, they form a black hole. That's the basic process that we'll be interested in. And of course, there's no reason why there should only be one black hole in the world. Two clouds of gas, somewhere in distant parts of the universe, could independently collapse and form two black holes. We could call one of them Alice's black hole. I suppose that's the one on the left. Bob's black hole, he's a little fellow. Can you see Bob? I can't, yeah, there's Bob. Bob, that's Bob's black hole. There's Alice's black hole over there. And just two black holes. What do they have to do with each other? Not much. They were formed independently. They're uncorrelated. They're not interacting with each other because they're too far away from each other. And so we would say that they're statistically and dynamically and in all ways independent of each other. No interactions, no correlations. And if perchance Alice happened to fall into her black hole, that would be the end of her. If Bob fell into his black hole, that would be the end of him. End of story. Okay? Now, what I want to imagine now is that we formed the black, well, no, let me come to, I am tired. Let me come to another issue now. That was black holes. We'll have more to say about black holes, clearly. But before we do, I want to talk about entanglement. Entanglement is the thing that Einstein, Podolsky, and Rosen discovered. Okay? What is entanglement? Entanglement between systems. It could be entanglement between two electrons. It could be entanglement between two photons. It could be entanglement between, well, any two things. Entanglement is a quantum mechanical, it's the quintessential quantum mechanical property that systems can have, pairs of systems, that never makes any sense classically. If I were to tell you that I know everything that there is to know about a pair of systems, these two things over here, if I know everything that can be known about the composite system made out of these two things, what are these things anyway? If I were to tell you that I know everything, or that everything that can be known about the system is known, you will say, well, that must mean that everything about the parts of the system are known. How can it possibly be that you know everything that can be known about a system and not also know everything about the two parts of the system? Well, in quantum mechanics, that can happen. You can know everything about a pair of electrons. This is supposed to be a pair of electron spins. The spin can be up or it can be down. Two electrons. And for those who know a little bit about entanglement, you'll recognize this as an entangled state in which You know nothing about the first particle. What do I mean by you know nothing about it? It could equally well be likely to be up or down. So if it's equally likely to be up or down, you know nothing. The second particle can equally well be down or up. Again, you know nothing. And yet this is as complete a description of this state of an electron, of a pair of electrons, as you can possibly have. What do you know? What you do know is correlation. You know that if the first electron is measured to be up, the second one is definitely down. If the first one is measured to be down, the second one is necessarily up. It's either this or this. That's the character of entanglement. Something that never happens classically. As I said, if you know everything there is to know about a system, you know everything about its parts. Not so quantum mechanically. Two particles which are entangled in this way are usually called Bell pairs. Bell doesn't stand for the thing that you make a sound with. John Bell, the physicist John Bell, who spoke about a great deal of this and added a great deal to it. But this is essentially the Einstein-Podolsky-Rosen idea of entanglement. And we usually use a little graphical notation to indicate that two particles are entangled, namely just draw a line between them, and that indicates that they're entangled in this funny way. Okay, now, let's imagine again that we're going to create two black holes, but instead of just creating them independently, what we're going to imagine is that we create first a bunch of Bell pairs, a large number of particles which are entangled with another large number of particles. This particle is entangled with this one's entangled with this one. We create them in the laboratory, and then we separate them. Separating them does nothing to destroy the entanglement. And so what we wind up with is two entangled clouds of particles, and then on each side, the particles collapse to form black holes. What does that make? Well, it makes two entangled black holes. That means that if you measure something about one black hole, you learn something about the other one. If you measure something about this one, you learn something about this one. Two entangled black holes, Einstein-Podolsky-Rosen entanglement, in this case between black holes. And this is something that, it's not something you're going to do in a laboratory. We're not going to make blacks in a laboratory. But in principle, this is something that could be made. Okay. What's new about it? How are the entangled black holes different than the unentangled black holes? And here is where something strange happens. I'm not going to prove it. I'm going to tell you this is the outcome of many years of research, the last 20 years of research, 20, 25 years of research. We'll talk a little bit about it. But I'm going to tell you right now what has been learned. Now, take a look at this. This is supposed to be space. Why have I bent it over like that? Bending it over like that does nothing real to it. If I have a piece of paper and that piece of paper is flat, if I bend it like that, that does not change the geometry of the sheet of paper. The intrinsic, it's called the intrinsic geometry. The intrinsic geometry is the same whether it's this way or this way or this way, or this way. But just so I can make a point, I've taken space and folded it over so that this region over here is close to that region on the diagram. These two places are very far apart. If Alice wants to get to Bob, she has to walk all the ways around here. Alice and Bob have created a pair of entangled black holes. The new thing, because they're entangled, is that an Einstein-Rosen bridge forms between them. An Einstein-Rosen bridge is popularly called a wormhole. It's a route through space which short-circuits the long distance between these. This is, to my mind, one of the craziest things we've discovered in the last 20 years. That the existence of entanglement creates spatial connectivity between two regions which would otherwise be very, very far apart. Now, does that mean, does that mean that Alice can send a signal to Bob, short-circuiting the long distance between them? No, it doesn't. Entanglement does not provide a way of sending messages. It's correlation, but it's not message sending. Alice cannot, when we're going to come to the reason why, soon enough, why Alice can't use this wormhole, this Einstein-Rosen bridge, to send a message directly to Bob. She cannot violate the rule that to send a signal from one place to another place, that it goes faster than the speed of light. It would be going faster than the speed of light, at least the speed of light around this direction, if Alice could send a message to Bob. There are two ways to think about this. From the point of view of entanglement, there's a theorem. The theorem says that entanglement can never be used to send a signal from one place to another. It's correlation, but it's not signal sending. From the point of view of general relativity, from the point of view of these wormholes, it's the non-traversable character of wormholes that you cannot cross from one to the other, from one side to the other. I'll explain why that's true, but not yet. Okay. But nevertheless, despite the fact that Alice and Bob cannot send messages through the wormhole, there is something else that's extremely odd. And this is a property of general relativity. It's a property of these Einstein-Rosen bridges, namely that Alice and Bob can decide to jump into their respective black holes and meet at the center. So let's just review. We take these entangled particles, we separate them out to the ends of the universe, we collapse them into black holes, and then Alice jumps into her black hole, Bob jumps into his black hole, and they can meet in the center after a very short time. That is a remarkable conclusion if it's true. But the only thing, whoops, let's go back. The only thing is that their meeting at the center can never be, how shall I say, can never be reported to the outside. They are stuck behind the horizons of these black holes. They've jumped in, they're behind the horizons of the black holes, and they cannot report to the outside world that they've discovered each other on the inside. So somebody on the outside will not experience any indication that something very strange has happened because of this entanglement. Okay, for the experts. Here's the proof. The proof is a Penrose diagram. If you've seen Penrose diagrams before, you'll know what this is. If you haven't, it's just what I said on the previous slide. This is a picture, a diagram, a mathematical diagram of the two black holes that were created very, very far apart, but in which you can pass from one to another through a wormhole. What this picture is saying, what the previous picture is saying, is that Bob and Alice can jump into their respective black holes and meet at the center. All right, so that's a mathematical proof. Did you catch the proof? No equations, but a mathematical proof that two entangled black holes, and they are entangled, two entangled black holes can be used not to send a message through. Notice, you cannot send a message from this side over here to this side over here. That would exceed the speed of light, but the two participants can jump in and meet at the center. That's a crazy thing. Good. It is crazy. Given that it's crazy, you might ask, and you might sensibly ask, how can I have the boldness to be so sure that such things are right? Do I really know what I'm talking about? I'm making up things. Maybe I'm making up things. I do make up things sometimes. No, I'm not making up things. All of this comes from about 25 years of experience, combined experience of 25 years of many physicists. It began with something called the holographic principle, which I won't go into. I was involved in it heavily, but it's part of the story. We won't go there right now. The holographic principle in another language is called, I warned you I'm tired. It's called gauge gravity duality. I'll talk about that a little more. One version of it is called matrix theory. It goes back to 1996. But most of all, the most important thing that goes into these arguments is something called ADS-CFT. I'm going to tell you what that is. It was discovered by Juan Maldacena in 1998, and it has been the main driver of research in quantum gravity for at least the last, I would say, the last 20 years. I think 20 years, yeah. And it has been extraordinarily fruitful. So let me tell you what it is. The holographic principle is the idea that a region of space can be described by degrees of freedom and physics on the boundary of the region of space. That idea became extremely precise with the work of Maldacena. And here's what it says. It says in a kind of space called ADS. ADS stands for anti-de Sitter. There's a kind of space called de Sitter space, and it was invented by de Sitter. This was the space that was invented by de Sitter's aunt. Sorry. It's anti-de Sitter. It's the opposite of de Sitter space. Whatever de Sitter space is, this is the opposite. But this is the way to think about it. It's a space-time. Time runs upward, space runs across, and it's a space that you can think of. You can think of it as being in a finite cavity in a finite spherical box with reflecting walls so that anything that hits the wall of the box bounces off. Everything takes place within this box. Time runs up, space runs across, and it's a space-time that has gravity in it. It can have black holes. It can have people. The people can fall toward the black holes, and it's called the bulk space. It's three-dimensional. I wrote D-dimensional here, but it's three-dimensional space in here. The holographic principle, or ADS-CFT, says exactly this state, this system, is equally described mathematically by a theory of degrees of freedom that live on the boundary of the space, purely on the boundary, and those degrees of freedom constitute a quantum field theory. A quantum field theory whose degrees of freedom are entirely restricted to the boundary of space. That quantum field theory has Feynman diagrams and particles and so forth, but they don't move into the bulk. They live only on the boundary. And Maldacena's discovery is that these two theories are exactly the same and describe the same thing. That is also crazy, but here the mathematics is extremely precise, and so I will assume it's true. The things I'm going to tell you are consequences of this idea. You don't have to believe any of them, but if you don't believe them, I think you have to not believe in this kind of gauge, gravity, or ADS-CFT duality, which, as I said, is mathematically very precise. Okay. Good. Now where are we going to go next? Next, what I want to tell you is the kind of quantum field theory that describes the boundary of space, or that, sorry, it doesn't describe the boundary, it describes everything inside the space, but it lives on the boundary. It's a field theory on the boundary. That kind of quantum field theory is a very familiar kind of quantum field theory, but it occurs, usually you think of quantum field theory as having to do with elementary particles. But the place where quantum field theory also really has had a tremendous impact in physics is in condensed matter physics. Just a lump of material, if it's quantum mechanical, and of course all lumps of material are quantum mechanical, are typically described by quantum field theories. Those quantum field theories, for example, can govern the phonons propagating in a crystal lattice, the fluctuations of a superfluid, superconductors, magnetic systems, quantum Hall system, topological insulators. And those quantum field theories are very similar to the kind of quantum field theories that go into this gauge-gravity duality, the kind of quantum field theories that live on the boundary of space. In fact, there's no known objection or obstruction to engineering a strongly coupled large N gauge theory on a shell of silicon. You'd have to dope the silicon, you'd have to put in some extra stuff. But this, when I say silicon, it doesn't have to be silicon. That's just a metaphor for a piece of material. Constructing a set of degrees of freedom that live on a shell that have the property of behaving exactly like the kind of quantum field theory that gauge-gravity duality is all about. So I want you to imagine that we created such a shell in a laboratory. There's our shell of matter. It's a shell, it's hollow, there's nothing inside it. And it has been engineered in just such a way that it is described, all of its properties are described by a quantum field theory that lives on that shell that has just the properties of the kind that Maldacena thought about when he talked about the relation between anti-de Sitter space and the boundary quantum field theory. So there it is. And now Alice, who is the experimentalist in this laboratory, wants to check, is there, in some sense, an equivalence between the things that go on this shell and some kind of theory that lives in a bulk, in a hypothetical bulk? I'm not going to tell you where the bulk is, but we'll ask. All right? So she's going to do some experiments on the shell. The first thing she does with the shell is she taps on it. Tapping on it will create excitations on it. Now, from the point of view of the shell, looking at the shell, you might expect that the perturbations create waves which go around the shell and focus at the opposite end. It's true, that's what would happen. On the other hand, if you were a believer in the existence of a bulk, then you might say that tapping on the shell over here shoots a particle into the bulk, which propagates across to the other side. In both cases, you'll find that something goes across from this end to this end in a certain amount of time. And in fact, if you calculate in the anti-de Sitter space geometry how long it takes for a signal to go through the bulk, it's exactly the same as the time that it takes to go around the boundary. So that's a check. Alice does this. She taps on it over here. She goes and looks over here, and she says, oh my goodness, something came through the bulk, or she can say something went through the boundary. No difference. She can do other kinds of experiments. In fact, she can get together with Bob. Alice will tap on this end, Bob will tap on that end. That will create signals which, according to the bulk theory, propagate into the interior from both sides, scatter as if they were particles scattering, and then come back out to the boundary. And if Alice waits over here, she will see a signal over here, and Bob will see a signal over here. What will they conclude? Either there was some rather magical conspiracy in stuff propagating around the boundary, or they will say, yes, there is this bulk boundary correspondence, and one way to think about it is by tapping on the shell, we send something into this hypothetical bulk which scattered off the other thing, and they wound up near the boundary. One can calculate these things, and in fact, that is what they would see. Here's another example. For some reason, I imagined two taps, one from over here, one from over here. Now, in this case, we imagine that there was something already in the bulk. What does it mean that there's something in the bulk from the point of view of the boundary? Don't worry. Somehow, some energy was sent into the system so that some kind of object is believed to be, by Alice. Alice believes there's some kind of object at the center of the bulk of the geometry here. And so she taps on the system. That creates a signal that goes into the bulk, if you believe in the bulk, hits the object over here, and if the object is of the right kind, it might start it ringing. If it was a bell, it would start it ringing. If it rang, it would send out waves. The waves would propagate out to the boundary, and by standing out near the boundary of this shell here, the boundary out near the boundary, she would discover that some kind of waves propagated out. She would feel it. She would be able to detect these waves hitting the boundary. And she would conclude that, yes, there was something at the center. It had some properties, and they could be probed from the boundary, from her outside laboratory, by tapping on the shell. So the lesson to be learned here is that Alice can either think that the boundary theory created waves which went around the boundary in very, very complicated ways, or she can think equally well that yes, there really is a bulk on the inside of the shell, and that stuff can propagate in, hit things, scatter, and be detected at the boundary. Now, one of the things that we can create in the bulk is a black hole. How do we create a black hole? I'll just have to tell you this. The way you create a black hole, starting with just the shell of silicon, you heat it up. That's all. You heat it up. Just heating it up creates energy on the shell. And the dual description of that, the description of that from the point of view of this ADS-CFT holographic description, is that a black hole is, it's obvious, but that's one of the things that goes with this idea. How can you heat the shell? One way you can heat the shell is just illuminate it with laser until it's heated. It creates a black hole inside the bulk. Of course, you can't see behind the black hole horizon for the usual reason. Nothing can escape from the black hole. But you could do other experiments. Having created the black hole, you could hit it with something and watch the black hole ring. Black holes do ring. They have quasi-normal modes, which are like ringing modes. So Alice could, in fact, attempt to discover whether there's really a black hole at the center of this shell, and she would discover that there is. We could create two black holes. Same way, right, we could create two shells. Let's start with two shells. We create two shells. And again, illuminate each one separately, create two black holes, and that's all. We just have two black holes, two independent black holes in two different shells. But we can do something else, or at least Alice can do something else. She can use a phenomenon called spontaneous parametric down conversion. Spontaneous down conversion is a process in which a photon, an electromagnetic photon, a high frequency one, or a relatively high frequency, that's why it's labeled with blue, hits a crystal and splits into two photons. It's a nonlinear process. One photon becomes two photons, but moreover, the two photons are entangled. Entangled the same way that Einstein talked about. Then go and be absorbed by the two separate silicon shells, and both will get heated. But now, by virtue of the fact that the photons which heated them were entangled, the two shells, or the two black holes, will also be entangled. Well, we argued a few minutes ago that entangled black holes have Einstein-Rosen bridges between them. They're connected by wormholes. Alice and Bob can attempt to send things into the silicon shells. There are two silicon shells. Remember, one is over there, one is way over here. They can send surrogates into the shells by tapping on them, by doing things. Those surrogates can fall into their respective black holes, And the prediction is crazy again, that they will find each other and meet each other inside the two black holes. Now, these aren't real black holes. At least they don't seem like they're real black holes. They're just descriptions of the behavior of these silicon shells. Descriptions of the behavior through this idea of gauge-gravity duality. But yet, if you believe the mathematics of gauge-gravity duality, you're forced to conclude that Alice and Bob can send in signals. They may even be able to worm their own ways into these shells and meet at the center of black holes which aren't even really there. Or at least nobody can find them in the laboratory. There's two laboratories, there's the two shells. Nobody in the laboratory can find this wormhole which connects them, but yet they will find each other. That's the prediction, that's the crazy prediction. Can it be tested? Can it be tested given that the surrogates or Alice and Bob themselves only meet behind the horizon? And the answer is yes, it can be. Here, I'll show you what they have to do. I've abstracted the whole picture of the two black holes and their wormholes by just drawing a wormhole between two circles over here. These are two horizons, the two horizons of Alice's and Bob's black hole inside their respective silicon. And here's what Alice wants to do. She has some kind of system in her possession. It's a quantum system. It could be a spin pointing in some direction. Whatever it is, she wants to send that to Bob as a message or as a present. She wants to send it through the wormhole to Bob. Now, can she do it? I will tell you the answer is yes. She can do it by a procedure, which goes as follows. The first thing she does, let me go back. The first thing she does is she drops the quantum system that she wants to send in into her black hole. Okay, that sends it into the black hole, into the wormhole between them. Then she makes a measurement of some kind. She measures something on her horizon. This is the horizon of her black hole. She measures a couple of things. It almost doesn't matter what she measures. She makes some measurements, and she records them in her notebook. Maybe just a few numbers that she measures about her black hole. Then she sends her notebook to Bob. Now, first of all, what's in Alice's notebook is pure gibberish. It's random. She made these measurements, quantum measurements on the system. She just got random gibberish. Why? Just because that's the way these quantum measurements would work. She gets random rubbish, and in particular, that rubbish has no correlation or no memory to the system that she threw into the black hole. But when Bob gets it, he has gotten something which you can think of as a code for what to do next. He gets this little piece of information which itself has no information about what Alice sent in, but it gives Bob an instruction what to do next. Bob follows the instruction, whatever it is. He applies his instruction to his black hole. Maybe he rotates a magnet, maybe he bounces a ping pong ball off his black hole, whatever the instruction is that Alice sent. And guess what happens next? The quantum system that Alice sent in pops out on Bob's side. The message went through the wormhole. Doing this with the two silicon shells, Alice and Bob can convince themselves that indeed there was a wormhole and that the system, the present that Alice sent to Bob, passed through the wormhole. Okay. Moreover, in passing through the wormhole, whatever that system was, it may detect things inside the wormhole. There may be photons in there, there may be other particles. when whatever it was that Alice sent through comes out the other side, it may have been affected by the things that were discovered inside the black hole. And so when it goes through the wormhole and comes out the other end, whatever that system is, it records a message that can be delivered to Bob saying, I found this or that inside the wormhole. So not only can you send the message, but you can explore the wormhole. Now, is this fantasy? Is it just a concoction that I made up? No. It's actually called quantum teleportation. Quantum teleportation is a procedure that was invented not by gravitational physicists, not by ADS, CFT, Maldesanes, and so forth. It was invented by computer scientists, quantum computer scientists, who were interested in exploring quantum mechanical ways to send very secure messages, messages that could not be eavesdropped upon. This is the sort of iconic figure of quantum teleportation. Alice and Bob create a pair of entangled particles. There's an extra particle over here, which Alice on her side wants to send through to Bob. When I say a particle to send through to Bob, I mean the quantum state of the particle. She has a particle and a quantum state, and she wants to send that quantum state to Bob. This is the iconic figure. Again, Alice combines the system that she's trying to send with her half of the entangled system, makes a measurement, sends a couple of pieces of classical information, and Bob then knows what to do so that his qubit over here comes out in the state of the thing that she was trying to send through. This is called quantum teleportation. It's a thing that has been done in the laboratory by now. It's a hard thing to do, but it has been done in the laboratory. And you can ask, how did the information get from this side to this side? It did not go through this classical stuff that was sent across here. That was gibberish. One can say, either you can say, well, it's just quantum teleportation, or you can say it passed through a sort of proto-wormhole that corresponded to the fact that you have entanglement between these two things. You can do the same thing, except in a much more elaborate way, which much, much more reflects what happens in these black hole prototypes that were made in the silicon shells, not by using silicon shells, but by using quantum computers. If we ever develop quantum computers, this time goes up in this picture. This is supposed to be a quantum computer processing information by interacting with each other. Here's another computer over here. What goes on down here is simply the statement that the two quantum computers were made out of entangled matter. You've entangled two quantum computers. This is something that can be done. I mean, in principle, it can be done. Probably in practice can be done. Two quantum computers can be entangled in this way. You can add a couple of degrees of freedom, a couple of qubits on Alice's side, and let them interact with the rest of the quantum computer. And if you do the protocol correctly, out will pop whatever you put in over here on Bob's side. You have your choice. You can either say this is just quantum teleportation, nothing new, or you can say that the entanglement created a wormhole between these two, and this system over here went through the wormhole and popped out on this side over here. The two descriptions are quite equivalent. You can do something else. You can modify the initial state of the quantum computer. I've just done one extra little perturbation over here. Somebody gives a little knock to one of these qubits over here. What does that do? Well, it just affects the quantum computer in a certain way. But from the point of view of the black hole picture or the wormhole picture, this perturbation over here is roughly equivalent to making a new photon or a new particle inside the wormhole. You perturb the wormhole, it's a little bit different. Perhaps it has an extra photon. The effect of this perturbation over here will influence what comes out on the right-hand side. Instead of the system going through and coming out unmolested, let's say, it will be affected by this. Another way to say it is when you send something through the wormhole, when it comes out, it has a record of what it encountered in the interior, which it can report to the outside. In other words, it allows you to explore the interior of the wormhole. And this is something that, in my opinion, will actually take place in laboratories. When we learn to build quantum computers, there's no reason why this can't be done in a laboratory. If we have more than a few qubits, it will be impossible to study by the standard quantum mechanical methods. How will we study it? By thinking of it as a gravitational wormhole. Okay. Now, how long have I been going on? Okay, we have a few more minutes. I wish I had my glasses. Yeah, okay. Yeah, I began by telling you there were two things that made me think that quantum mechanics and gravity are so tightly connected together that they really can't be separated. One of them was this ER equals EPR. Einstein-Rosen Bridges, that's a gravitational thing. EPR, that's a quantum mechanical thing, and they seem to be the same. The other thing, which is very interesting, I think, is the idea, of quantum complexity and the growth or the expansion of space. Wormholes grow. I'll show you a little cartoon that I made to show you that wormholes grow. If I have a wormhole, there's a wormhole connecting two otherwise distant places. What happens in time to that wormhole? That wormhole starts to grow. Applause. Thank you. The wormhole grows. This is a consequence of Einstein's equations of motion for the gravitational field. Wormholes grow. Okay, I'm going to do it again, but I'm going to put a little extra something in. I'm going to imagine that when we started, there was a particle on the left side, Alice's side, and Alice wants to send the particle through to Bob while the wormhole is growing. Watch what happens. The wormhole never gets through. Sorry, the particle never gets through because the wormhole is growing. The particle can't keep up with the growth of the wormhole, and the result is you cannot, this is the non-traversability of wormholes. Why can't you traverse them? Because they grow at such a rate that you get frustrated, the particle can't get through by the time the wormhole is separated. This is the gravitational origin, or when I say gravitational, I mean the general relativity origin of the fact that wormholes are not traversable, that you can't send signals through them. The quantum mechanical explanation is the statement that entanglement does not allow communication, or doesn't, Oops, one more. I'll do it once more. I like doing this. No applause that time. Okay. All right, what I just described to you, I'm going to show you in a technical language, the language of Penrose diagrams. Penrose diagrams are a technical way of describing the geometry of space-time. Here, for those who know, again, this is for those who know, this is the Penrose diagram of two black holes connected by entanglement. On the left side here, this is Alice out here, this is Bob out here, and this is only for those who know what I'm talking about. If you don't know, it's just what I previously said. And what the picture is supposed to do is convince you that I know what I'm talking about. Okay. All right, this is Alice's side. Here's the outside of Alice's black hole. Here's the outside of Bob's black hole. Good. And the entanglement between them somehow creates a new region of space that you can think of as the wormhole. Here's the wormhole over here. Okay, let's take a look here. Notice that the wormhole grows. This is time. Time goes up. The wormhole grows with time. It's small over here. It gets bigger. It gets bigger. It gets bigger. It gets bigger. The question is, what is it from the point of view of quantum mechanics, which is growing when a black hole, when the wormhole inside a black hole grows? This is a question that should have been asked 20, 30, 40 years ago, and for some reason or another, nobody asked it. Let me go back a step and talk about another thing which grows, another thing which we do know what it is that grows. Here's another Penrose diagram. This is a traditional Penrose diagram for an ordinary black hole that's been created by a shell of incoming matter. Again, I apologize for those who are not familiar with Penrose diagrams, but I'll try to explain what's going on. Here's the interior of the black hole. Here's the exterior of the black hole. Here's the horizon. The horizon starts small, and it grows. Not this distance, but the area of the horizon grows. The black hole starts small and starts to grow, and it grows until the shell of matter passes the horizon, and then it stops growing. Do we know what's growing in this case? I mean, we know the area of the horizon is growing, but do we know from a quantum mechanical perspective what's growing? Yes, we do. It's entropy. It's the entropy of the black hole. And in fact, the fact that the area of black holes always grows is nothing but the second law of thermodynamics. Entropy grows with time, and entropy is area. Okay, now let's come back to this issue of what is it that's growing on the inside of a black hole in the Einstein-Rosen Bridge? What is it that's growing when the Einstein-Rosen Bridge grows? Okay. Is it entropy? No, it's definitely not entropy for two reasons. First of all, these two black holes were in thermal equilibrium to begin with. You'll have to accept that these two black holes were in perfect thermal equilibrium, and their entropy will not grow. It's as large as it can be to begin with. And furthermore, it grows forever. This is T equals infinity out here. Or at least classically, it grows for a very, very long time, whereas entropy very quickly stops growing when a system comes to thermal equilibrium. A black hole comes to thermal equilibrium extremely rapidly, and so there's no chance that it's entropy that grows. What is it? Well, what it seems to be is something called quantum complexity. So I need to explain to you, I think we still have 10 minutes to explain what quantum complexity is and what it has to do with black holes. These are surprising ideas that are no more than 5 years old. The idea that complexity is what governs the growth of the space behind the horizon. Let's start with the difference, how different classical states. Think of a computer. The state of a computer is described by the state of a bunch of bits, zeros and ones. Okay? To describe the state of a register inside a computer or a memory, it's just described by a series of zeros and ones. A set of binary digits, if there are n bits, then there are n binary digits in the description of the state of the computer or the state of the memory of the computer. So it takes n binary digits to describe the state of n bits. What about a quantum register? A register made out of quantum mechanical qubits. How complicated is it? Well, each one of these states of the classical computer is itself a possible state of a quantum computer, but the most general state of a quantum computer is a superposition of these. Is a superposition, a quantum mechanical superposition, and it requires 2 to the n complex coefficients here to describe that quantum mechanical state. So, whereas this took n binary digits to describe the corresponding quantum mechanical state requires 2 to the nth complex coefficients. Here, the number of distinct classical states was 2 to the n. Here, the number of corresponding quantum states is e to the 2 to the n. So quantum states are vastly richer and their potential for complexity than the corresponding classical things. How do we describe? Is complexity just a, what is complexity? Complexity can mean all sorts of things to all kinds of people. My relationship with my mother-in-law is complex. All sorts of things it can mean. But by complexity, we mean something very, very definite. It's called computational complexity, computational quantum complexity. Again, we imagine a quantum computer. It's running, time goes horizontally now. You put an input into the quantum computer, and then the qubits interact with each other. These little red circles here are called gates, logical gates. And the computer processes the initial state. The initial state could be a bunch of zeros. That's a simple state. It processes them and spits out a quantum state of some more complex character. The definition of complexity is the minimum number of gates that it takes, the complexity of psi. Starting with something simple and easy to describe, how many gates does it take, the minimum number, to get you to the state of interest? That minimum number is called the quantum computational complexity of psi. It's a property of the state of the system. How complex is it? How hard is it to make? Okay, so it's the minimum number of gates. Now, the maximum entropy of a system of n bits, or even n qubits, is n. The maximal complexity is 2 to the n. So complexity is a kind of thing which can grow to a vastly bigger size than entropy, and that's why it continues to grow for very, very long periods of time after a system has come to thermal equilibrium. This is something computer scientists, and in particular quantum computer scientists, did know. Mostly physicists didn't know it. All right, so the hypothesis, and this hypothesis fits extremely well, that the growing wormhole, that the size of the wormhole in here, the volume of it, is described quantum mechanically in terms of the complexity of the state of the system. The relationship is that the volume of the wormhole divided by Newton's constant times a certain length scale, which has to do with anti-de Sitter spaces and so forth, is equal to the complexity. And this has been a fairly well-tested hypothesis, and it's surprising. Again, it's surprising because it's another link between quantum information on the one hand, something purely quantum mechanical, and something purely relativistic, or general relativity, the space behind the horizon. Okay, so we have these two aspects. On the one hand, the growth of the volume of the wormhole. On the other hand, the growth of complexity in a quantum mechanical system as it evolves. Again, a tight-knit, close connection between quantum mechanics and gravity, which 5 years ago or 6 years ago was totally unexpected. Can Alice and Bob measure the fact that the complexity is increasing of their wormhole? Yeah, they can. Here's what they have to do. In a quantum mechanical theory, the vacuum fluctuates. There are field fluctuations, electromagnetic field fluctuations, whatever. Typically, they fluctuate so that if in one place the field gets a little bigger, in some other place it goes in the opposite direction. So there's constant, and they're correlated. If I take field fluctuations in one region of space, forget the wormhole for a minute. These are just two very distant places. Forget the wormhole. The field fluctuates over here. Alice measures those fluctuations. The field fluctuates over here, whatever field it is. It fluctuates over here. Bob, oh, that's Alice. No, that's Alice. That's Bob. Sorry, Alice. Alice and Bob measure the fields in their neighborhood. They fluctuate, they go up and down. They're too far apart to compare the fluctuations, but they can measure them and they can record them. They can keep track of the time at which the fluctuation of the field, of the electric field, went up, the time at which it went down. They can keep a record of it. Now, the first thing that they find because of these entangled black holes, oh, well, let's go slow. Because of the large separation between Alice and Bob, these fluctuations, the fluctuations are there, but the correlation between them would be very weak. They're so far apart that there's hardly any correlation. Distance between things is a measure of how strong the correlation is. On the other hand, in this circumstance, with this entangled pair of black holes, Alice and Bob would discover, essentially as the status of a theorem, that the correlations are not as small as they might have discovered because of the long distance between these. In fact, the correlation starts out large. Okay? And with time, the correlation falls. Why does the correlation large to begin with? Because there's another route between Alice and Bob where correlations can propagate between the other route, namely the wormhole. Because the wormhole is there, the correlation between Alice's and Bob's measurements is large. On the other hand, because the wormhole grows with time and they separate, that correlation will get smaller and smaller. L here is the distance through the wormhole between Alice and Bob, and that's the way we expect the correlation between Alice and Bob to decrease. On the other hand, we can study complexity in a purely quantum mechanical context, and we would discover that the correlation between two quantum computers would also do the same kind of thing as the complexity increased. As the complexity of the system increased, we would also find that correlation decreases. They have exactly the same form. One of these is a general relativity prediction having to do with the growth of space. The other is a quantum circuit or a quantum mechanical, what a quantum computer expert would calculate, and he would also calculate the same kind of thing and basically get the same answer. Now, Alice and Bob, what are they going to do with their information? Alice has recorded the fields, the fluctuations in her notebook. She's timed them. It went up over here, it went down at this time, it went up at this time. Bob has done the same thing, but there's nothing they can do with that unless they can talk to each other. And typically they can't talk to each other through the wormhole, but what they can do is after they make the record, the long tabled record of the fluctuations that they've witnessed, after the experiment is over, now I love doing this. Hooray for Bob and Alice. Bob can take the long route, bring his information over to Alice, and they can check that the correlation functions decreased in a certain manner, and then in fact it reflected the growing complexity. You can do the same thing with quantum circuits, or you don't need silicon shells to do it, you don't need black holes to do it. You can do the same kind of thing with entangled quantum circuits or quantum computers, and you'll find the same behavior. What does this tell us? Well, one interpretation is just quantum mechanics made the correlation decrease because that's a calculation you can do without having anything to do with black holes or anything at all. Or you can discover and notice that the way the correlation decreases is exactly as if there was a wormhole between these and the wormhole grew with time. My main message here, I would say, is, well, okay. We have 5 more minutes? 2 more minutes. Then I won't try to do the next thing. I'll just tell you what I think the upshot is. The thing which is, to me, most exciting now about this, and which I think should provoke some response from experimental physicists, is that it appears that in this way of thinking, you actually can do experiments which have the status of experiments on quantum gravity. You do not have to have very heavy objects. You do not have to have Planck scale accelerators. you need silicon shells, or better yet, quantum computers that can simulate those silicon shells. When I say silicon, as I said, the silicon is a metaphor. And doing the right kind of experiments, testing this ADS-CFT connection is, in a sense, doing experiments that are testing ideas which are ideas of the connections between quantum mechanics and gravity. The claim is that any experiment of this kind will be consistently interpretable either as a quantum mechanical experiment or as an experiment involving space, time, and gravity, wormholes, whatever you have. There are many examples of this. I've only touched the surface. I won't go into them here. You can come back and ask me about that if it, yeah. Okay, you can come back and ask me about these pictures if you want to ask questions. But I think the main thing that I wanted to emphasize is this possibility in the future, and the relatively near future, I think, of actually doing experiments which bear directly on the quantum theory of gravity. That is something that I find exciting. Okay, I have described a point of view. It's my point of view. It's a point of view which I am responsible for, responsible not in the sense that I necessarily invented it, but if it's wrong, I will take responsibility for it. You know, like my president said, I'll take responsibility. I'm not sure you know what I'm talking about. But I will say these ideas were extremely heavily influenced by other people, and in particular, very, very influenced by two of my colleagues, one of whom is Joe Polchinski, who terribly, unfortunately, is no longer with us. This is a great blow to physics, to me personally, and to everybody who knew Joe. I think I would like to dedicate this lecture to Joe Polchinski, who died prematurely, and to Juan Maldacena, who is alive and kicking and doing wonderful physics. I think these two people, more than anybody, have contributed to my own views about these things. I think it would be too much for me to claim that they shared the same views. I would be putting words in their mouth. But yes, they did share the same views. Okay, so good. We can stop here.